Right, hi everyone. So this video is all about putting all of our hypothesis testing together. So like we did in class, I'm going to summarize how binomial and normal distribution two-tailed tests are very similar to each other, so that way you've got this structure for your notes, for your revision. So we've done that before, but then the last part of the video is to talk about PMCC, so hypothesis testing for zero correlation. So the standard for you, the H0 will be that something doesn't have any correlation, and then if it falls into a critical region, then it means it does have correlation. So that's going to be the last part of the video. For now though, we'll just recap again on how we structure our hypothesis testing. It's always the same. Okay, I'm going to do it for two-tailed tests. So over a period of time, Agatha has discovered that carrots that she grows has a 25% chance of being longer than 7 centimeters. She tries a new type of fertilizer. In a random sample of 30 carrots, 13 are longer than 7. Longer than 7? 13? Agatha claims that the new fertilizer has changed the probability of a carrot being longer than 7. Test the claim. Okay, so H0, H1 is always our standard. The fact that we've read the words change, that means different, and that means P is not equal to 0.25, because our chance of it being that is 0.25. We always write assume H0 true, such that, and then we'll say what the binomial is. So there are a sample of 30 carrots, and chance of success is 0.25. Okay? And then, because remember what we're doing, we've got some distribution, binomial distribution here. We've got two-tailed tests, so there's between 0 and some number x1 contains, as 5% is the significance level, we half it, so 2.5% is in there. And similarly, there's some number x2 to 30, because 30 is the maximum number of carrots we can have, where the other 2.5% is contained. And if our data falls into this critical regions, one of those critical regions, then we reject H0 and accept our new hypothesis. Okay? So remember what we're doing. We're trying to find that x1 and we're trying to find that x2, like so, our regions. So we're going to always the same. X is less than or equal to x1 is less than half of our probability. And the same this side, but greater than x2 is again less than half of our probability. Remember, we can just now go straight to x is less than or equal to x2 take 1. It's bigger than 0.975. So this is because it's a binomial, this x2 take 1. Think about what this means. This is x2, x2 plus 1, x2 plus 2, etc. But before that is x2 take 1, x2 take 2, etc. So, very quickly, how can we go from this to this? We know that's the same as 1 minus x less than or equal to x2 take 1 is less than 0.025. We can subtract the 1 from both sides, so x less than or equal to x2 take 1 is less than minus 0.975. Divide by the minus 1, which flips the signs over. Okay? So that's why I don't bother writing that anymore, and I just go straight to less than or equal to and flip the sign over. So we go to our list function in our calculator and we find what that value x1 is. Unfortunately, I can't get the emulator working because the subscriptions run out. Typical. So we go to, you can do it at the same time, so we go normal CD, we go to list, we type in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, probably up to 20. But yeah, you can go all the way up to 30. N is 30 when you press equals. The probability of success is 0.25. So we look down our list and we're looking for the first value x1 that will give us less than 0.025. So it looks to me like it's 2, because this is the same, so I'd write equals 0.0105, which is less than 0.025. So we've got a critical region already, because our critical value is x1 is 2, and remember it's x1 to 0, so 0, x1 to 2 is our first critical region. Now we just need to do the second side. So we go to our list again and we're looking for the first value, which is bigger than 0.975. So that looks like 12. So less than or equal to 12, I write what it equals to, and that is bigger than 975. So therefore, x2 take 1, remember, is 12. So x2 is 13, and therefore that's our critical value. Our critical region from our diagram here is x2 all the way up to 30. So 13 less than or equal to x2 up to 30. So there we go, we found our critical regions. This is always the method we're going to use, critical regions, okay? So we've got our conclusive steps then. So they found that 13 were longer than 7. 13 is in the critical region. So 13 were longer, and 13 is in the critical region. So you first say 13 is or is not in critical region. Our second line is the contextual side. So as it's in the critical region, you can say sufficient evidence to suggest length of caret is different. Is different or has changed, okay? And then final step is, do you accept or reject H0? So we say accept H1, okay? So cool, that one's done, binomial. So we should be pretty okay with that. Now let's go for, whoops. Cool, now let's go for the normal distribution one. So as we talked about in class, this is the thing that you have to remember, where n is the sample size, okay? And what you're talking about is you're testing the mean of your product and then saying whether that mean is justified for the whole of the population. So you've got a sample mean. This is what we found in the sample. Is that therefore enough to say, well, the mean of the whole population must be this way? Okay, and we talked about that more in detail in class. So really, I'm just talking about the procedure here. So what we need to do is, again, we need an H0 and we need an H1. So we're talking about the mean because we're in normal distribution hypothesis testing. And so the mean of the population, in this case, it says, let's go through the data, claims that the mean mu is 60, okay? And then a trading inspector claims that it's different to what they say it to be. So it's not equal to 60, yeah? We go straight for our assume. You notice I haven't really even read everything. I'm just following a process. So assume H not true, such that, again, notice the line's exactly the same, such that this time X bar, though, is the thing that we're looking at, is a normal. And now we're following this formula. So the mean we're talking about was 60. That's this one here. And then we've got our standard deviation squared over n. So what is n? Is the sample size. So sample of 16 cartons. So there's n. Square root, we've got standard deviation squared. So where's the standard deviation? 3. So 3 squared, and this is all squared on the outside. So I'm just following that formula. If you don't know the formula, you're stuffed, aren't you? You're stuffed. So just like the binomial, we've got an upper tail, except we're looking at mean bar. We're looking at x bar, remember, x1. And again, we've got a less than, and what's our significance? 5%, so half it, 0.025 again. And this one, we've got an upper tail. Again, is less than 0.025. But where this is our mean in our calculator, and this part is our standard deviation in our calculator. So really, like I say, I'm just talking about procedure here. I'm not really talking about the y's and stuff. Just like before, we need to make it less than or equal to, because we need inverse normal and our calculators work left to right. But unlike binomial, we don't need a -1 here, because this is continuous data for normal distribution. Okay, so this is more than 0.975. I'm just keeping the notation the same, so it's easier for you to remember when you're doing binomial or normal. But whether it's less than or equal to here is completely irrelevant to whether it doesn't matter if it's less than or equal to, because it's continuous data, and so the equal to bit will equal 0. So I go to my calculator, again, so I don't have the emulator. We just go inverse normal, 0.025 is our area, and we're subbing in these constraints. So we should get our critical value becomes x bar equals to, and if I go to, so you can do it along with me, number 7, it would be good if you did do it with me. Number 3, which is inverse normal, our area is 0.025, our standard deviation is square root of 9 by 16, and our mean is 60. So 58.5300, and then that's our critical value x1. So therefore our critical region is everything between 0 and next one, 58.53. But that's only because you can't have like a negative amount of juice. Like in, you know what I mean? It's sufficient to say that it's just less than this because normal distribution goes on for infinity. Okay. And the same time here, we've got our x2, so our critical value. What is x2 bar? Well, that's, again, we need our inverse area. And this time our area is 0.975. So we go 0.975, and that is 61.46997, etc. So therefore our critical region is everything bigger than that. So bigger than or equal to that, 0.46997. Okay? Cool, so you see it's very little difference apart from knowing the formula here and also not doing that x2 take 1 thing here because this is continuous values. So our conclusive step is the same. It's the same process. Is the thing in the critical region or not? So they found the mean juice was 59.1. So 59.1 not in critical region. Therefore, sufficient evidence to suggest mean juice in population, that's the important thing, is not different to 60, okay, because that was the original thing, it said 60. And then the last point then is, do you accept or reject H0? So we will accept H0 because nothing's changed. It wasn't in the critical region. Okay, so that's all old hat. We've done that stuff before. Now, new stuff, and it's actually, you'll be relieved, this is quite easy, to be honest. It's very easy and very procedural. So this time, hypothesis testing for zero correlation. So essentially, what happens is, you're going to have a bunch of observations. So you can see here, scientist takes 30 observations. So this is our n. Okay, so n equals 30 of the masses of two reactants in an experiment. She calculates a product moment correlation coefficient. So that's our PMCC of r equals minus 0.45. So the important thing is that this is a sample. The sample generated this R value, and what we're trying to say is, does the whole population follow that correlation? Is it reasonable to say, well, because the sample had this R value, therefore the whole population will have a similar R value or has some kind of correlation? Do you see? So it says the scientist believes there is no correlation between the masses of the two reactants. So no correlation, terms like test whether there is correlation, or test if there's any evidence of correlation, as I've written up here, okay? Or test that there is linear correlation, means a two-tailed test, because it hasn't gone either way. It hasn't said it's positive or negative, okay? So just like before, we've got an H0 and an H1. Now the R is our sample PMCC, but our population, okay, population PMCC is denoted as rho. So that's kind of a skewed looking P. So rho in this case is 0. And for H1, we're saying it's not 0. So the established view at the moment, H0, that's our null hypothesis. The established view is that the population has no correlation. H1 though says actually it's not zero correlation. There is correlation somewhere, whether it's bigger or less than 0. Okay, and that's what we're trying to find out. So what we do is then we say, what's our sample size? Our sample size is 30. And what you've got to the right here is a table, and this is what you're going to have in your exam and what you're going to use in class, is a table of all the pre-calculated R results. And really we're going to use this. There's a hell of a lot of complicated maths behind this table. All right, and it used to be we'd give you tables for binomial distribution and null distribution stuff, and now our calculators can do that all for us. Our calculators have not done this population mean, this population correlation coefficient calculation. So we are back to using tables for this part. This is a new part. This wasn't in the old A level, okay? So what we do is we're going to read off this table. So it's the same idea. We've got our n equals 30, we've got our hypothesis stated, all right? And you can write assume true, if you want, that h naught, or assume true h naught, see what it means, such that rho is equal to 0 or something like that. But you don't need to write that at all in this one, okay? So all you're going to do, it says 10% significance level. So just like before, we have a lower tail and an upper tail. So what we're going to do is we're going to go to n equals 30. We're going to go to 10%. So 10% is here. N equals 30 is here. So we're looking at this number here, all right, because we're at 10%. So what we're saying is that the critical region is that R, because it's a two-tailed test, right, yeah, sorry, as this is a two-tailed test, I shouldn't be looking at 10%, I should be looking at 5% per tail. So actually, it's this one. So I'll do that in blue, sorry. So it's this one here. Okay, so 0.3061. So our critical region is plus or minus this. So for 0.05 per tail, okay, R is either less than minus 0.3061, right, that's our lower tail, or critical region R is bigger than positive 0.3061. Okay, so we stated our critical regions, and where does our observation lie? R equals minus 0.45, so that is less than minus 0.3061. So again, we have our conclusive step. So minus 0.45 is in critical region. So therefore, we can infer from a context, therefore, you can say that the masses of two reactants has evidence of correlation. But we don't even need to say if it's positive or negative correlation, because H0 just said there is no correlation, but actually we found that there is some correlation. So therefore we say accept or reject H1. So we're going to say accept H1, okay, because it was in the critical region. We'll do another example of that. So remember the two-tailed test, we have to split the significance level up. So I nearly fell foul of that. It's going too fast. So you must split that up and read it off that table. Let's do another example here, and then that will finish the video off. Okay. So I hope this is useful because you have everything kind of together now. You've got all your hypothesis testing together. So the following table shows the marks attained by 8 students in English and maths here. Okay, so calculate product moment correlation coefficient. So this is a good chance for you to do this in your calculator at the same time as me. So you go to stats, you go to number 2, you've got X and Y. So you go 25, 18, 32, 27, 21, 35, 28, 30, and then we've got our Y lot of stuff. So this is 16, 11, 20, 17, 15, 26, 32, 20. Okay, options 4, and we get R is 0.6856 for sig fig. Okay, and this is interesting. So what this is saying is, where it seems from our sample that if you're good at English, then there's some relationship saying that you're going to be good at maths. And is that true or not? We're not sure. So that's what part B is about. So it says test at 5% significance whether these results show evidence of positive linear relationship. So if it just said of linear relationship, then that means a two-tailed test. But as it says positive, then it's a one-tailed test. It has put a stance on it. Okay, so you got H0, H1. So H0, we got rho again. Rho is our population parameter for R. So is not is equal to 0 because there's no correlation thought to be. And this was saying that there is positive correlation. So remember, this R is our sample PMCC, and we want to see if we can infer from that that the population has the same kind of relationship, so the same kind of correlation. So how many, what's our n's, what's our sample size? 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. So again, we need to establish our critical regions, and we do that by looking at the table. So n is 8 here, and we're looking at a significance level of 5%, so that's here. So we're at 0.6215, and as it's greater than 0 here, we're looking at more than. So R is more than 0.6215. Okay, so there's our critical region established. So again, we go into our conclusion. So you see, it's so much easier than the other two. Where does 0.6856 lie? That is bigger, so we say 0.6856 is in critical region. Therefore, back into context suggests there is a positive linear relationship between maths, between marks in English and in maths. Okay, and then again, last step, do we accept or reject? So we're going to accept our H1. Okay, i.e. there is a positive correlation for the whole population. If you're better at English, you're better at maths. Okay, that's the end of that one. So hopefully this has helped with the overall hypothesis testing revision for everything.